All right, so we are on. Mm, and welcome again, everyone. As usual, we are going to go with these three problems, which we do every day nowadays. We will start with easy problem, then medium, and then the hard one. And there is no time constraint or anything as such, but we will try to have some time, spend lesser time on easy so that in the end we have some time to talk about at least harder problem. So if I say, hey, let's hold on for a minute, just think okay, this is just to make sure that everybody gets benefit out of their time and also to make sure that we cover all the three questions.
Yeah, and then maybe for the variation of the question, we can hold it to the end, so we have time to go over, all the question.
Yeah, yeah. And feel free to stop me in between and wait for me to hopefully I can answer it in, if I know the answer and it is very trivial, I will answer right away, or we can talk in our channel about it later. Or if it is totally irrelevant, we can again discuss it after the session, so everybody gets benefit out of that time. So I think we can start with the first question because it's 8:33. So the problem is factorial trailing zeros. You are given an integer and you have to find the number of trailing zeros. So for example, for factorial 3, it's 1 into 2 into 3, which means 6. There is no trailing zero. For factorial 5, there is 1 because it is 120. So how many of you have tried to solve it? I wish I could see the participants while I'm talking. But when I'm sharing this screen, I can't find how to see the participants. So let me stop share. Let me try to share my screen and then yeah, if anyone can raise their hand, we can talk about the approach and then we can go from there.
Hey Roger, you can see the participants while sharing the your screen as well. You just need to go to the more option of that, and there you can see the participants.
Oh, I see. So from here, I should still go to share. Oh, I see here. Where is that? More. This one?
Actually, we can't see that where what you are getting, but it's over there only that you can see
Yeah.
participants.
Yeah, there is a manage participants. It comes as a pop-up, but it's fine. Okay, no problem. Let's play with it for some time. So guys, anyone want to talk about their approach if they have solved the first problem, factorial?
So I haven't solved it, but I can give a try.
Sure.
Uh, like we know the factorial formula. If we do go for the factorials and it's a brute force, we can go for finding the factorial, and after getting a number, we can just need to check the last digits, like how many times our zeros are there for that particular number.
Yeah, that's a nice start actually. But yes, anyone else has sees the problem or any better way to do it?
Yeah, I think what we need to do in this problem is we need to find the number of fives actually. Whenever, if I have a number, let's say 20. So what I need to find more is how many number of fives, it means like how many numbers that are divisible by 5 are available before 20. Because every 5 will come with some 2 or 4. That way, upon multiplying, we'll get a 10 for sure.
Okay.
So somehow we need to calculate the number of fives that we'll have, till we compute the factorial. So in that way, we won't need to, to compute the whole factorial, but we could do that only by somehow dividing the number by 5 repeatedly.
Mm-hmm.
Maybe some that way. I didn't code it, but that was the thing that struck into my mind as soon as I
Sure.
saw the.
Yeah, I mean, idea seems pretty good. And anyone has any question on this idea? Like, I can start sharing my screen and we will go over it so that we, okay, why I'm going there.
So I actually solved the way Sonia said, like
Mm-hmm.
calculating the factorial. This is Smita, calculating the factorial and then finding the end zeros. The problem, I got a lot of test cases wrong. One was because I was taking integer and it was crossing the limit, integer limit. Then I tried with long. Even with that,
Mm-hmm.
it was crossing the limit that the long integer because it goes exponentially. So I
Right.
couldn't come to the resolution for that. So then I started looking into discuss and I came across the solution that was just mentioned by Yash, I guess.
So can we make that the result whatever we got in a string and then we can calculate the zero with it? That's a long approach, but can we do that as well?
Sure. So that's a good question. So what you are doing, like, is basically factorial n, you are going through 1 into 2 up to n, right? And then you just calculate it and then you divide by 0 and then you get all the leftover values. So suppose it was just something 12,000, then you will count these three things because you keep dividing by 10, right? That's your approach. And the problem was overflow, and also it may not fit in the number range. So some of the languages actually they provide you ways to store that as a string. So for example, in Java you have big integer, you can use that, and it will do internally it will do the string conversion to store the numbers, and you can divide it by big int 10 after you get your result, and you can still make it work. So yes, it is possible if you use big int, but yeah, we don't have to use it as someone explained that when we do this factorial thing. Okay, any question on this approach first of all, then we will talk about the better approach.
No question.
Okay, good. So now uh, we had an example factorial 3, which was basically 1 into 2 into 3, and its value is 6, right? Easy. Factorial
Yeah,
5 was 1 into 2 into 3 into 4 into 5, and it is
120.
120. Yeah,
Yeah.
120. And what he realized that, hey, 5 is coming here and 2 is coming here, so these two guys combine to give me 10. That is the observation he did. And so now the question is, who is the main contributor? Is it 2 or is it 5?
That's
So
5 actually.
good, very nice. And why 5 is the major contributor?
Because every time there'll occur a 5 or 15 or maybe something, it will, it will succeed 2 or 4 or a even digit number, which will multiply to give a 10.
Right. That's a very nice way. So if you try to draw a frequency for 5 and 2, 2 occurs more frequently, right? So
Yeah.
every time 5 occurs, 4 already has occurred. So it can borrow 2 from the one previous guy. And there are so many even numbers, it can choose any one to generate 10 at the end,
Yeah.
right?
Yeah.
Good. So we can keep doing that. So next thing comes when you try to calculate factorial 25, because this way we can say, hey, if I have to calculate factorial 15, factorial 15, then you just keep dividing by 5. I know 5 comes 3
Three.
times. So you will have 3 zeros, right?
Yeah.
I'm sorry, can you explain why we use 2 again? Because I can say like 2 times 5, 10, 4 times 5, 20, 8 times 5, 40. So that all, we have a lot of zero in there. But, out of 2, 4, 6, or 8, why we have to select 2s?
You can select, for example, here, you can select 4 also, right? If you select 4, you are getting 20, right? If you just select 4 here. But what we care about, if we choose any even number in place of 4 or 2, you can select 6 if you were ahead. The net result is you will get 1 0. That is the constant thing here, right?
Okay.
So 5 needs one even number to generate 10. Let's call 5 is a producer, and to generate like any 0, it needs any even number. Doesn't matter which that even number is.
Right. But it's not like cumulative, like 5 times 2 and then later 5 times 4, 5 times 6, or
No,
5 times
no,
8.
no, it's not cumulative. It's not cumulative. I'm just showing you that it will choose one pair. Any even number is a, like, you can choose with 5, and it's a property of 5 that if you multiply 5 with any even number, you will get a 0 at the end.
Okay.
So that was one thing. So for factorial 15, similarly, how many times you will get 5? You will get 5, and then you will start getting into 6, into 7, into 8, 9, 10, into 11, 12, 13, 14, into 15. Sorry. So this was 1 5. This 10 is again, like, it has 1 5 inside it. 15 has 1 5 inside it. So you have 3 5s. So you can generate 3 zeros, because each of these guys can pair up with one even number preceding them, and they can generate 1 0 in your result. But the problem, or things are interesting when you start with factorial 25, because in case of that, you will have, after 24, you will have 25, and 25 is 5 into 5. So this guy has not just 1 5, it has 2 5. So this 5 can multiply with one of the even guy, and this 5 can also go and multiply with any even guy, and can generate actually 2 zeros, not just 1 0. So that is the, core of this algorithm. Like, after 25, you have to, like, you can't say that, hey, just dividing by 5 is good enough. You keep dividing by 5 unless you get a, like, mm, product of 5, and that's how you can generate the factorial. Any questions? Like,
No questions.
it's good then. So yeah, that is the main idea. And let me see, can you see my code already or not? I have to
No.
stop. Okay, so I have to stop share. I don't want to show code, but it's a small code, so why not? Like, okay, share screen. Exactly what we just talked about. We have this number n, and we keep dividing by 5, and we keep accumulating the result, and then we just return the result. So that's it. I mean,
So, where in this code we handle a case like 25?
yeah. Yeah, it will handle a case of 25.
One question. So if we have a 3, can it handle that case as well? Like before 5, let's say 4, we
Yes, and
5
Yeah,
is
it will return zero because the while
result
loop is
is zero.
only the numbers when n is greater than one. Sorry. Result won't update, I guess.
What's the question? Sorry. Like, what should I take as example? 3, you're saying?
yeah, yeah.
So when 3 comes, then you will not actually, result will say 0 here, right? Because dividing 3 by 5 will be 0. And then that number is again, like, you are out of loop at this point of time. So you will say there are 0 trailing zeros.
Oh, okay, okay, got it.
Yeah. So
And it can handle 25 as well.
yeah, if it is 25, so this will be, first of all, it will have 5, right? And this number will change to 5, right? Because 25 by 5 is 5. So
Yeah.
it will again go inside loop once, because 5 is greater than 1. So you will add 1. So this will become 6, and then n will become 5 by 5 is, like, it will out of this loop, and then you have accumulated 6 here. You can play with the code. It's like, idea. If you were clear about the idea, you can write it in any way. um, make sure you are dividing, because when you have to choose between dividing or multiplying, you can avoid overflow if you choose to divide. So that is one good way to, you know do the same thing, I would say, to avoid surprises. Any question on this problem, or we can move to the new one, or any other ideas? That is fine.
Yeah, so basically, when we are dividing n repeatedly by 5, we are handling such cases when we'll get 25 or 125 or 625. We are
Yeah.
handling those cases by the line number 7, I guess. Am I
Yes.
right?
Right.
Okay, thank you.
Great. So let's do the next question then. I think we are done with this, unless someone wants to share any other approach. I like the first approach, by the way. I was thinking about that too. That what if we want to just use the definition of the factorial? But yeah, it's good that we brought it up.
But that will even, exceed the time limit, I guess, for the big numbers, for large
I
numbers.
haven't tried. Yeah, I haven't tried, but yes, maybe. I mean,
Yeah, but
problems should be that, like, yeah, actually it's written, your solution should be in logarithmic time complexity.
yeah, and that will
So it
take big of unnecessary.
so it already tells you something that, hey, don't go with O of n at all. Yeah, that's a good one. Okay, any questions before we move to the next question?
I think we should move to the no nobody prompted yet.
Okay, let's go. Let's write this. So this question, medium, cheapest flight within K stops. So you are given number of nodes. You can call it cities, like, this is 0th city, this is first city, this is second city. And the cost between traveling from 0 to 1 is 100. Cost between traveling from 1 to 2 is 100. And from 0 to 2, it is 500. And you have to give the least price, right? If you are okay to have k number of like stops in between. So when you look at this problem, I want to get an idea what you think. Don't think about the solution, just think about the problem. What comes to your mind? like couple of things which just like, gives you some, what is this?
So this looks like a graph problem to me.
Okay, that's a good, yeah, it's a good observation.
So
Anyone
here,
else? Yeah, go ahead.
where every node is a city and connected by edges, and then there are some weights.
Right. So we can call it, it's a weighted graph. Is that right?
Mhm. Yeah.
So yeah, we are closer to a lot of things. Weighted graph.
Mhm.
If we want to, yeah, if you want to generalize it, it's a weighted graph for sure. Plus, if you come here, and there is another example. So you have nodes in the range, that is fine, size of light, and then see this line. There will not be any duplicated flights or self cycles, right? So this is a directed weighted graph without a cycle. So we haven't thought about solving this problem yet. I'm trying to tell you that how the problems can give you some insight what to use. So I'm trying to focus on that part of the problem. Another thing is, okay, weighted graph without cycle. Now what? Also, can I say that all the flights will be like, will have positive edges here? Because cost is not going to be negative, at least realistically. And it's also given in this example, by the way. The price of each flight is actually positive, right?
Yep.
So now we have a directed positive weight graph without a cycle. And we are trying to calculate like, least price, or you can say like in terms of graph, least cost from certain source to destination. Forget about K for now. So does that give you now directly a solution? If it doesn't, it's fine, because maybe it's possible you might have forgotten about it, or you might haven't thought about it yet, but you will, like, after this session, hopefully you will remember it. Anyone has any idea? Like, we have transformed this to a standard problem actually. You are given a graph, weighted graph, no cycles, positive edges, from a source to destination. We want to find the like cost.
I
So
guess we could use Dijkstra algorithm. Some
yeah, Prim's or Dijkstra, like where we want to find the small, shortest distance with
shortest path. Yeah.
weight based on the
Exactly.
weight.
Yeah, exactly. What does Dijkstra do? It does exactly the same thing. As long as you don't have a negative cycle, you can apply Dijkstra on weighted graph. I mean, that is the sole purpose of Dijkstra.
Yeah, but
So
I guess the stopping criteria here is, that K which is given. There's a cap on the number of stops that the flight can take.
yes, right, right. That is true. So that is one extra thing you have to check when you try to do Dijkstra, because in Dijkstra there is no limits, right? You can just without like, looking at K, you can continue your traversal. But here, when you are including your next uh, possible node to visit, you have to make sure, hey, like, is it within the bound? Like, am I more than like, K places already? Like K stops I have already traveled. If I have traveled, then it is not the right candidate for this problem. So
Yeah.
other than like, that extra check, it's standard Dijkstra problem. I mean, one way to solve it. I'm not saying this is the only way, but if you know Dijkstra, if you read it in this way, then it will tell you what you want to do. So On the approach side, does anyone has any problem? Or understanding the problem is itself, if you have any question, feel free to ask now. I guess it's clear. Okay. If it is clear, then again, I don't want to go to the code, but since somebody asked, yeah, go ahead.
Can we make a walkthrough of this?
Code, you're saying?
Like an approach of this?
Sure. Yeah, we can. We can. So let's try this. Stop. Okay. So you have been given a graph. Maybe the first problem was something like this. Like you had, oh, I have to learn this. Where is pen? Does anyone know where is the pen? I have tried once, I again forgot. Is it? Oh, maybe this one. Yeah. So suppose this is how our graph used to look. So this was 0, this is 1, this is 2, weight was 100, 200, and 500. And this is the source. And this is the destination, right? We can have a value of k equal to 2. Okay, so we start like, if we are doing Dijkstra, we start at this node, 0th node, and we see all the neighbors of source where we can go to. So in the beginning, you will have something like this in your result. Like, so your 0, 1, 2, this will have value 0. I'm talking about a standard Dijkstra, not just particular to this problem. So then you can map to this solution. This will have infinity, this will have infinity. Now from 0, where can you go? Like if you look at its neighbor, and I'm assuming you have already built the adjacency matrix or graph for the representation. You know that you can go to 1 and 2 with some cost, and then you can go to 1 if with 100, right? Because it was 0 plus 100. If you want to go to 2, you will have this value of 500, right? You can keep it in a priority queue, for example. So Dijkstra is using priority queue because it's like a greedy based algorithm that it will only choose the value which has the least cost so far. So from 100, you can go to 2 with basically 200, which means price 300. It will add it into this queue. So this queue will have value 300 and 500 if you think we added it. So in the priority queue, 300 will be on top because it's a min heap. And we will check, we are already at destination. So we will just exit the loop that, hey, we are already at destination. So don't check even this guy at all, even though we could have reached here using 500. wait. Does that give you a brief overview, or if you want to explore any particular part, let me know. I
No,
can really.
I got it. Yeah.
Okay. So yeah, here now you think that if k was just 1, for example, now let's say k was 1, I or maybe k was just 0 actually, because 0 means you have to directly reach there. Then what would happen? You you can go from 0 to 1 after paying price 100, 0 to 2 after paying price 500. That is fine. But when we are going to in-queue its next candidate, we popped it from our queue, 100 was less, so we started adding its neighbor. We check, hey, my value is k equal to 0. So there's no point adding my neighbors because I have already used the maximum allowed stops. So actually pop it out and do nothing. You are done. So now 500 gets out. And then 500, it looks at, am I at the destination? Yes, if I am at destination, then I'm done. If not, then it would have chose its neighbor, which in this particular case, there is no neighbor. So, so that's it actually. So that is the,
Uh,
yeah, go
yeah,
ahead.
Roger, one question. So
Mhm.
let's say if there exists another path from 1 to 0, right?
Okay, okay.
So when I come to 1, I find like there is a path for 1 to 0. I started traversing that also. So do we need to keep visited? I mean, some site where we are taking care of like which node we visited so far, that kind of thing in this algo.
So in, so make sure there is no loop here. Like, and the question says that there is no loop, right?
No, it says no self cycle.
No, no self cycle.
Yeah.
So,
So no cycle from 0 to 0, there will be no path, or 1 to 1, there will be no path. But this cycle can exist.
okay, suppose like this was 100 and from 0 to, from 1 to 0, how much price do you want me to pay? 100 maybe?
100 only, yeah.
Okay. So, okay. Suppose even if you don't add your like visited check here,
Yeah,
you are reaching from 1 to 0 again, and now you have paid price 200, right?
yeah,
And your K has already increased.
yeah. K will be 2 now.
K equal to 2 now.
Yeah,
And in your queue, you can keep doing this back and forth if you want, but maybe you are not doing that still, because when you are here, you already have added this guy also,
yeah.
right?
Yeah, I mean, I will ultimately exhaust based on value of K, because after K becomes 0, I already traverse number of path 2. I will
Mhm.
not continue going in this cycle. But I was
Right.
thinking like, how do we need to keep visited, or it is required? Because if in a long graph we have multiple such option, and
Yes,
we
yes.
will be
Yeah,
wasting resources. So that's why I was thinking if we
true.
need base. Yeah.
Yeah, you
Actually,
hope, go ahead.
yeah, actually, in Dijkstra algorithm, we check our neighbors. The shortest path possible to the neighbors from our place, as well as the previous cases. So I don't think we'll necessarily, loop through 0 to 1 and then back from 1 to 0 in Dijkstra algorithm, because it is quite efficient. And the thing about k is there was already given that k, it was the upper cap of the k. There's nothing like we can't go in one stop there. So we don't even need to travel like back and forth from one position to the other position, because it will be, charging us the money only, as it is given that the charges are never negative. They're always positive.
Yeah, he
So
was talking more about optimization, like you can always optimize if you know that you are at the same place multiple times, and you you know that you are going to inquire more cost, then maybe you don't even do that. For example, like like what's the problem with Dijkstra, by the way? Like we were talking about all these positive cases, like uh why not negative cycles are solved by Dijkstra?
Maybe because that will lead to self loop, or sorry, not self loop, but that will go into an infinite loop going from one position to the other again and again. No, but visited array would help me counter that. I don't know.
But we are
So
not considering visited array in Dijkstra, right?
yeah, we are not considering that.
Yeah.
It will work without that, because the problem says that there is no
Yeah.
self loop, and also there is k is
Yeah.
there.
K will
So
exhaust.
yeah, so anyway, like since we are talking about this, like let's understand a little bit more. So here, 1, 2, 3. This is my source, this is my destination, for example. What is the cost from source to destination? It's 6, right?
Yeah.
It's a linked list, simple linked list, which is a graph. Now, if there is a self loop or call negative edge, like choose something here, like -4, for example. Then what is the cost from source to destination? If I choose to loop once, will be 6 minus 4, basically, right? 2. If I choose to do it one more time, this will become 2 minus 4 minus 2.
Yeah.
And Dijkstra will have no idea what is going on.
Yeah.
Yeah.
So you will continue to fall in this trap. So now the thing is what to do. Like maybe for this particular problem, there is not a problem. How do you solve, like if the problem is a different problem with negative edges?
Yeah. Then visited thing will help us there.
Or we can like in this case we go how many times, right? Let's say we go maximum we can go like k time. So we limit the number of edges we can traverse.
Yeah, but sometimes you will have no k also, and then you will have no idea. So for that particular case, there are other algorithms like that's, I'm just giving you a brief revision. Basically, there is a like Bellman-Ford algorithm. It it detects that like negative edge it can handle. It detects negative loop. So if you are doing a single source shortest path algorithm, which Dijkstra is doing, and it has negative edge, you would probably choose Bellman-Ford algorithm. And if you are doing all pair shortest path, like from one place to all the other neighbors, and from from basically all neighbors to all nodes to all node, what is the least cost? Then there is Floyd-Warshall algorithm, which have higher time complexity, but it is totally based on dynamic programming approach. So you will choose that algorithm. So given you know that there is a graph, you have to also understand when would you apply which particular algorithm, what it is best suited for. Why I'm applying Dijkstra if Bellman-Ford is able to solve both the problems with negative edge and as well as this problem because of the time complexity. So just giving you an overview when to choose what. I can give this, I can share this after the like meeting so that you can, just put in your notes if you want.
Yeah. Sure.
Yeah. Any other problem on this? Any other question? Did anyone try to solve it directly using DFS or BFS?
Yeah. I use this, but I was getting time limit exceed.
Mm-hmm.
And then I thought like might be I'm wasting resource, and then this visited thing comes to my mind. I started using visited node.
Yeah.
So then I got stuck in another problem because I was storing in set, so I'm not able to traverse all the nodes because my set contain all the elements, all the
Mm-hmm.
nodes. I need
Yeah.
to clear set somehow when I reach to the final destination. So I was struggling there. I'm still working on it. Yeah.
Yeah, it's actually good approach. Like,
Yeah.
and it will work if you prune it, because eventually you are going to the same state again and again.
Again and again, yeah.
But yeah, but not, let's not call it a state. Let's call it same node, but state is changed.
Yeah.
How? Because now you have two dimensions. One is your node, and one is how many times you have used your, like, x out of k you have used when you reached a certain node, same place.
Yeah. So I
Right?
need actually, I have some idea, like I should use some data structure where I will keep neighbors instead of going DFS every time. That's
Yeah.
what I was thinking, yeah, but not able to succeed till now.
Actually, I have done using that BFS only, like uh, taking
Yeah.
that.
So did you prune it? Maybe you might have to do some, like,
Yeah.
exhaust some searches, like you have to get rid of some candidates which will not give you a better result anyway, maybe.
Yeah.
Or it will take more time, depends on how the problem is set. But it's good that, yeah, we talked about all these approaches. And by the way, just to complete this thing, I was thinking, so any regular graph is a weighted graph, right? My
Yep.
handwriting is not good here, but here we can say, like, all these edge has equal weight. So when we see shortest path, BFS should come to our mind directly. Only difference between BFS and Dijkstra, or, like, these kind of problems, like, algo we discussed, is now the weight is not one. So if I was here, I have no worry. Like, if I reach here directly from here, I know I will pay price one, because every node has equal weight. Like, it's uh, like nobody carries more weight. Like, it's like our voting system. Like, whether you are a PhD or if you have no knowledge, like, your vote is equal. Whether that is right or not, that's a different thing. But if this was 10, then, and if there was a, like, this kind of edge also, then we can reach faster. But then we would select this route if we are focusing on least cost. If we are trying to be more like, distance, like, I just don't care about cost because I'm too rich, I would still choose this one. So I have more, like, dimensions to worry about. So that's the way, like, we can think about it, and then we can probably move to the next question. I just wanted to show the similarity between BFS and Dijkstra, where they try to diverge actually.
Yeah.
Okay. Go to the last problem, or somebody wants to see the code. I can share the code later. So it's a standard Dijkstra algorithm, or actually there are a lot of solutions on LeetCode, so you can look there too. Okay. So no questions. Let's move to the last question then. I don't know who liked it. Clear all right. Let's go to stop sharing. And where is the problem? Share screen. Okay. This is a this is an interesting problem. Okay. So the thing is, you start going north, then you take left turn, then you take left turn, then you take left turn, you continue taking left turns. And you have to tell whether you have crossed the path or not. So, and this two means, like, you are going, like, 2 units towards north, then one means 1 unit to its left, then one means 1 unit to its left, which means going down basically, and then two means again going 2 units to your right, which means like east direction, let's say. So in this particular case, we are actually crossing ourselves. In the another example, if we go like this, we are not crossing it. Similarly, in this example, even if you touch, actually, it considers that you have crossed it because it went here with 1 unit, 1 unit, 1 unit, and 1 unit. So even if you touch your starting point, you consider that you have crossed the limit. So the problem seems pretty easy to understand what we want to do. Anybody tried this problem?
Yeah, I think that we go counterclockwise, right? And then we go the whole circle counterclockwise.
Mhm.
So my initial idea was like, if we want it to cut, when we go up, up, then the like the value that we go up had to be same or greater than. No, I mean, let's say the value that we go down had to be same or greater than the value that we go up. Similarly, if we go left,
Mm-hmm.
and the value that we go right have to be greater than or equal to the value that we go left.
Okay.
So, like for example, in example 2, we see in there.
Mm-hmm.
Oh, okay. The value that we go up, and then we go, when we go down, we go greater than the value that we go up, right? So that mean that we're not gonna meet, we're not gonna cross.
But you can continue going that way forever. So how would you? It is just showing you 4 values, but you can have many such values. So how would you deal with that? So you understand this is not the final value. Like you won't have 1, 2, 3, 4. This n can go up to, let's see, there is no limit, but the problem has it can have, I don't know, too many.
Oh, is it? I thought only 4.
No, no. Then it was not hard.
Yeah, that was the same thing I thought upon looking.
And
I
serious
thought it's
also. So
I even thought it's it's not for hard problems because that was pretty easy.
yeah.
Yeah, it
My
should.
intuition behind this was, if you could see, this is a kind of spiral problem. So there are only 2 ways a spiral can continue without intersecting.
Mm-hmm.
Either it is going inwards or it is going outwards.
Awesome. Mm-hmm.
And there's only, and if it's going outwards at a single point in time, it can turn inwards. But if it's going inwards, it can never turn outwards.
Awesome. Mm-hmm.
I think I might have confused a bit people, but
No,
if you just...
I will explain that. I will explain that concept. Thanks for bringing that up because it was not my idea. I did read about it. I did draw some diagrams to prove myself, and then
Yeah,
I
it's
will try.
as easy as it to explain inward and outward. The implementation and the corner scenarios of this are very hard.
Yes. So anyone else tried other ideas? Because I did also thought about this, after going through the solution, and we will discuss that anyway. But anyone else thought about any other ideas or tried this problem? Okay, probably not. So let's try. First of all, the brute force way of doing this because this is a good solution. So let's talk about it later. Like what you could do is these are all XY coordinates. You have many XY coordinates. So from 2 XY coordinates, you can say that I know a line, right? A line is basically X1, Y1, X2, Y2, and then you know entire details about that line. And these are horizontal and vertical lines. So we can figure out whether two lines are intersecting or not based on their value of x and y directly, right? Because your line could be like this. Suppose this is a vertical line. If this is a horizontal line, I know it will not intersect if I just check these x and y coordinates, right? Because it will lie inside this, or if it is a like vertical line like this and there is a horizontal line, I know that this will not intersect, something like that. So assume, and this is a smaller problem to solve. So assume you have this thing, a tool to figure out whether two lines are intersecting each other or not. How to solve this problem? Is that fine? Like we will go to the like next part of the solution.
Hello.
Go ahead.
Can you explain again?
So two lines, if they are horizontal, they will never cross each
Yeah,
other. That is fine because they will
yeah,
be
yeah,
parallel. But if
yeah,
two lines are like not parallel, so one perpendicular and another is horizontal, then how can we determine whether a line crosses the other line or not?
yeah, yeah,
You can check these coordinates and these coordinates to derive that, right?
yeah, yeah.
So it's like, after spending a couple of minutes, you will figure out how to do that. It's not the main
Yeah.
problem here. So suppose you have this figured out. Now what you can do, the brute force way is, since you have been given all this point, like, here to here to here to here to here, like something like this, you can continue putting this line into some storage, let's call it Q or something. And every time you add one line, we'll check whether it is crossing with the existing lines or not. So if I have to draw a more like, thing, when I'm drawing this line, I will check, hey, I will not worry about this line because I know I originated from this line. So it's not a problem. For when I'm adding this particular line, this line, I will check with, I will not check with like, horizontal line, because horizontal line is perpendicular. I will check with this particular line. I will check with this particular line, and I will check with this particular line, right? Because I'm keeping the coordinates, and I will keep doing that till I see if nobody has crossed this. We know that they didn't cross each other. That's a basic brute force approach. Like we are trying to simulate what was told without adding any intelligence to the like problem.
Why wouldn't we want to check the horizontal line? Because they could both on the same horizontal line, right?
Oh, you are saying why? Okay, you are saying if we were here and we
Yeah.
go like this.
Right.
So you are anyway checking with this guy, right? So it's,
Oh, okay, we already.
yeah, we are checking with
Okay,
vertical,
got
so
it.
he will catch it.
Yeah.
So this way you have one solution. If you draw multiple like, examples, you will figure out, because while you are making it larger and larger, like, like this, or smaller, you only care about last couple of the checks. Because see, now this guy, there is no need to check this guy if I am already checking this particular line, because it will totally have this smaller line inside it. Makes sense? Like when I am adding this line, if I just check with this line, or even actually with this line, there's not much like, after a certain depth, you can start to prune your, like, hey, don't even worry about after a depth of 5 or after a depth of 4, whatever. So you will not have all the points inside your queue. So your queue size is not growing like, exponentially or linearly even. Like you don't have to care about every time going to all the n values inside your queues. Don't go inside that. Just check last couple of 4, 5, and you're good. So your queue size then can be reduced anytime your queue size grows more than 5. Just drop these values. Sounds good? This is the brute force approach we are talking about with some optimization. We just added this optimization. And I will share the solution. It's on Discuss, so I don't have to write code. But after going through this, maybe that will make you more sense. So you can just go and read the solution, verify if you want. But conceptually, is there a problem?
Why do we need to check it with the previous 4, 5? Actually, we could do it with the last parallel edge. No, sorry, the last to last perpendicular edge, I guess.
So you are seeing only the happy path. Your stuff could be like.
Oh yeah, okay, got
Right.
it. But there could be multiple cases for that as well. Then we can't restrict to 5 even. No. Yeah, I got
No,
it. I got it.
you
We'll
got the
go.
idea. Like here now
Yeah,
you have a different new rules.
yeah,
You are in a different zone. So you will have to spend some time to make sure that, hey, actually those don't make sense. Like, don't check that, but that is an optimization. You can always go and select all the points
yeah,
if time complexity allows it. So that is the brute force way to simulate this algorithm, right?
yeah.
Now, if we are done, we can go to the actual good approach, or um, to learn from the pattern and then try to solve this problem.
Yep.
Yeah.
Great. So let's clear this. Okay. Give me 1 minute break, and then you guys can talk during that time if you have any questions, and then I will be back in 1 minute, guys.
So I just want to ask one question. So we only have 4 directions to move, or we can move like any directions? Like we have n number of.
Yeah, we can move in n number of directions. Actually, the examples show just 4, but you could make any sort of path. If there are multiple even after 4, then we'll go on, we'll keep on going in the counterclockwise direction with the units whichever it will be given.
Yeah. The direction will be 4, but the input can be a stream. So
Yeah,
any number of input integers will be keep coming, and you need to move based on the previous direction you moved.
Yeah, so we will be moving in 4 directions. Always we are going left from north. We start with north and keep going left. So there are 4 directions, and you can have any number of steps. So it's not just 4 steps. So any question on that? Was it Sonia?
Yeah, it's me. It was me.
Okay. So do you have any further questions before we start the other approach?
In the at the beginning, you mentioned there's a inward and outward. Can you elaborate on it?
Yeah, we are going with that approach now. So let's do that.
Okay.
Why not we go with that approach? So, happy case, like, you start like this. You start like this. So what you are doing is going outwards. That's what we are calling that. Hey, if I keep going, like, increasing my value 1, 2, 3, 4, 5, then I will never be in a problem, right? Because it's growing.
yeah,
So, right? So
Yeah.
this is one happy case. If you go like that, and if your input is like that, then like it's a sorted input, suppose 1 2 3 4 5 6 7 8, then you can say, hey, no problem. I will have no problem. I can just visit all the places. I'm not self-crossing. So how would you determine? It's like you will say that, okay, when do I know that I am not self-crossing is keep going outward. So if you check that wherever you are, like here, 3 and 1, let's look at it. So 3 is bigger than 1. So it determines that you are going outward, right? Because if 3 was less than 1, then if you, because you know that you will take a right turn from wherever you stop. So if I take a right turn here, I will cross this line eventually, or I may be trapped basically. But if I go further than this value 1, then most likely I am going outward. Actually, I am going outward. So all you are looking at, if I am at 4, I am looking at where was my horizontal last direction. So from 4, I can look at 2. If I'm going behind 2, then I'm going outward, right? So you keep going that. I think this is the implementation detail, but this is how you determine that you can go outward. Happy case 1. Next happy case, as someone was talking about, is when you go inward. So going inward means like opposite direction. You started like this, you started going like this. Still we are not self-crossing, right? Because we are going in this particular direction. Everything is fine. Till suppose this was my last point, I can say this is also a happy path. However, there is a difference between being happy in this first way and the second way. Can someone tell me what is that? We talked about it already. So the guy who suggested, he talked about it.
I think in the inward case, whenever we'll go outward, it will, it will be a self-crossing path.
Yeah. It's a good observation that when we are going inward, we are restricting ourselves, that now we cannot go outward no matter what we do, because we have made this circle towards ourselves. Where can you go from now? The only way to continue is you can continue growing inward, right?
Yeah.
But this guy, he can see what he can do. Like, this guy, he's growing outward, and suppose he decided to go inward, he can actually start a new cycle here. Something
Yeah.
like this he can do, right?
Would that be the same for the other case? Because you go inward, then you go outward, but you're not crossing, right?
From inward, how would you go outward? Because here, how would you go? Like, what will you do here? Like in this point?
No, yeah, no. I mean, you go outward, but you're not touching the other edge, and you go.
Oh, if you are not touching other end, then you are still going inward. Think
But you
about
go
it.
on opposite direction.
We can't go in opposite direction. Actually, we have been given with that data.
Oh, okay,
Like
okay.
counterclockwise direction all the time.
Does that make sense?
Yeah.
So the difference between these two happy cases is this observation, that if I am coming from outward to inward, it is still a good state. But once I go inside an inward trail, I cannot go outward. I have to continue going inward. So, okay, so that is one observation. Now, what can we do? Like, one place where you can start doing this is you can also go inward like this, right? I mean, just to make sure that. it's not just this particular case. You can also start going inward, like in this particular case. And whenever you go inward, there are certain cases you have to look at. So first of all, how would you determine that you are in an inward way, that you compare your previous to previous, like, direction, that am I trapped or not? You can go to the code to determine that. It's easy. But here, after you are in inward trail, now your boundary is not the same. See, your boundary is now, you are setting a new boundary for your trail basically. This is the maximum now you can travel in, because you are in that trap already. When we were going outward, we were just caring about, hey, what was my previous same direction distance? If I'm going with even 1 unit more than that, I'm in outward trail. So once you determine that you are not in that trail, you have to check your boundaries. Okay, what is my new boundary? If I update my new boundary, then we are again after updating the boundaries. So you update your boundary after detection. It may not be required. It may be required. We can talk about that case also, maybe. You are going to this happy case. So these two happy cases are pretty trivial to implement, as we can, we will post the question solution. And detecting this boundary is the crucial part of it, like how you detect that. Once you detect that, that okay, I'm out of this loop and I'm going into inward, let's reset boundary, and then just do these 3 steps. So your step is check whether you are going outward, first of all, outward. Then if not, because as long as I'm going outward, everything is fine, that's the best case, and it has more leverage that I can go inward but not the other way. Do I need to check my boundary? Check boundary, because now I'm not in my outward. So check boundary. After you check your boundary, then you start inward trail. So these 3 steps are there. Anyone has any questions or want to elaborate anything?
I thought like we check boundary when we go inward, right?
We check the boundaries in both cases, whether we go outward or inward, because how would you know that you are going outward? Without checking the boundary,
Okay, yeah.
you cannot determine that.
Mm.
But when that transition happens, then you now see, now this area is a different rule. This is not the same rule which these guys were having when they were going outward. Now his boundary is like limited to this particular area, right?
Right.
So that's why you do that check, and that guy's solution I can show you, and then let's, if you have more questions, we can just.
So that would be linear runtime?
Yeah. So exactly, this is what that guy was doing. I have also put the reference of this code. This is the code I was looking at.
Posted my solution also on the Slack.
Oh, nice. So same thing, we are keep going outward. We keep going inward here. And in between, we check whether we need to change the new boundary or not. And for that, you will do these checks. If you draw the picture, it will become evident what we mean. But if anyone has any problem, I can go and try to explain that too.
This is updating the input array also, right?
Yeah, it is updating the input array because here he just changed his boundary
Yeah.
here. This is the core point that he
Okay.
changed his next boundary, and that's it.
Okay.
Yeah, it was in math category, I guess. Related topics tells me math. So yeah, it was not any like algorithm data structure problem, but yeah, like it's interesting problem. Anyone has any questions or suggestions or anything? Or need more explanation?
No, I think we're good.
Okay.
I'm not sure how is this transition part working on.
Okay. So we can discuss it now if you have time, or I don't know, we are over the limit of like.
No, I can take a look. I can take a look at the link. If you could just post the discuss link on the Slack.
Yeah, if you debug, you can do that. But I have already done some research, so you can ask me maybe for particular example. I can give you that, so you can debug better.
We can stop recording and you can explain about it if we run out of time.
Sure. We can do that. So we are done with the question, overall question. So let me stop share and let's stop recording.